Yes.
Okay. Okay, I start. So hello, everyone. I am Andrea Pavan, and I'm a PhD student at the Padova University under the supervision of Dr. Riccardo Ciolfi. First of all, I like to thank all the organizers for letting me to cover this slot. And in this talk, I will discuss about short gamma reverse jet propagation in self-consistent binary star merger environments, which is one of the main topics on which our research group is currently working, and which represents a fundamental step to connect the electromagnetic observations of binary star mergers with the properties of the progenitor BNS system, and also, of course, of the jet that the latter is able to produce. So, firstly, I would like to highlight that during the multi-messenger event, W17 or 817, JB17 or 878, among the other things, we learned two important facts. First, that binary star mergers can power short gamma reverse jets. And second, that such jets do have an angular structure, which can strongly affect the electromagnetic observations of these events, especially in case of events with an off-axis gamma ray burst detection, as occurred for GRB17 or 78. However, how such a structure is formed is still a matter of investigation. Indeed, it could be related to the properties of the center energy that power the jet itself, or it could be also formed during the propagation process of the jet in the surrounding post-merger environment. And nowadays, to understand this, numerical relativity simulations play a critical role. In particular, high-resolution general relativistic binary star merger simulations are currently performed, understanding which is the role of magnetic fields, neutron star equation of state, neutron star spins, and neutrino radiation on the formation of an incident short gamma reverse jet. On the other hand, the large-scale jet propagation in the surrounding post-merger environment up to the formation of the observed electromagnetic signals is currently investigated by means of special relativistic or general relativistic hydro or magneto-hydrodynamic simulations, in which jet injection is manually performed using appropriate boundary conditions, or even self-consistently using initial conditions that are inspired by the result of the binary star merger simulations. However, both the binary star merger and short gamma reverse jet simulations present several limitations. In particular, jet production is still a challenging problem in binary star merger simulations. First, because these simulations have resolution problems which do not allow to, for the moment, to fully resolve all the mechanisms that are involved in the jet formation. For instance, magnetic field amplification mechanism. And also because these simulations are typically limited to space-time scales, which are often too small to reproduce the length of an incident short gamma reverse jet. On the other hand, the jet propagation studies are currently carried out using handmade initial conditions for the post-merger environment in which the jet propagates, and they lack of a direct connection with the realistic result of specific binary star merger simulations. So in order to establish at first connection between these two sets of simulations, the last year we published the first time short gamma reverse jet simulations, where we set up an initial propagation environment, which was self-consistently imported from a fully three-dimensional general relativistic hydrodynamic binary star merger simulation performed by our group. And we performed these our jet simulations using a special relativistic called Pluto, and adopting a three-dimensional spherical domain with an inner radial excision from the surface of which our incident jet was manually injected into the system. And here on the right, you can see some properties of our post-merger environment at the import time, which was set about 100 milliseconds after merger. And in particular, you can see in the plot on the left that this environment has an anisotropic resonance density distribution with the multiple shock systems and a low density funnel along the orbital axis of the central remnant of the merger. On the right, you can also see that this environment has a non-homologous radial velocity profile, in contrast with what's typically assumed in short-camera reverse jet simulations. So we perform our jet simulations in this paper using a simple top-head jet model with an initial two-side luminosity of 3 × 10⁵ arc per second, which decreases exponentially with time, with a time scale of 300 milliseconds, mimicking an accretion process that start to produce this jet. And we set the initial alpha Brownian angle of the jet to 10 degrees and the Lorentz factor to 3. And during this simulation, we took into account the Newtonian gravitational pull from the central compact remnant of the merger, whose mass was set the same as reproduced during the reference Barnstone merger simulation. In these plots on the right, you can see which are our final results in these jet simulations, and which correspond to about 1 second after jet launch. And you can see that at this time there is an enlarged jet propulsion system that reaches a spatial scale of 100,000 kilometers. And in particular, this system is characterized by a collimated head that moves a Lorentz factor of the order of 40, which is followed by a less collimated, less energetic and broken tail. And also in our previous paper, we studied the impact of adopting an ideal initial post-merger environment. And to do this, we performed the same jet simulations, but setting up an initial environment which has an isotropic density distribution and homologous radial expansion. And we found that in this case, the jet evolution is very different. In particular, there is a quite delayed breakout time of the jet from the surrounding environment. And the final jet is also more axisymmetric, more collimated, but also with a jet head that is less energetic compared to the case with the realistic environment. So this represented the first step to connect the Barnstone merger simulation with short-gamma reverse jet simulations. But these simulations didn't account for the presence of magnetic fields, which are known to play a critical role both during the merging process, but also during the jet evolution. So now I want to present you our more recent results, which concern the first time relativistic magneto-hydrodynamic jet simulations in subconstant magnetized Barnstone merger environments. In these simulations, we set up our initial environment by importing data directly from a fully three-dimensional general relativistic magneto-hydrodynamic Barnstone merger simulation performed by Dr. Cholti in 2020. And in these simulations, we set the computational domain as done in our previous paper using, again, the Pluto code. And we control the free divergence constraint of the magnetic field by means of the hyperbolic divergence screening method. In this plot on the right, you can see some properties of the magnetized post-merger environment imported into Pluto. This environment is imported about 150 milliseconds after merger, and it is very different compared to the previous one. And this is mostly due to the presence of the magnetic fields during the Barnstone merger simulation. In particular, this environment is about twice more massive. It is more expanded, and its magnetic field structure is very chaotic, especially close to the central remnant of the merger. And away from the latter, the field lines almost follow the distribution of the outflow material, accumulating in such arc-like structures, which are present also in the density profile here, and which increase the poloidal to toroidal magnetic field ratio at the larger scales. So in this new set of simulations, we aim also to extend the jet launching time in order to investigate more the role of the jet environment interplay in the overall jet evolution. And to do this, we exploit the fact that our Barnstone merger simulation is extended up to 255 milliseconds after the merger. In particular, to do this, we first extrapolate in time with Pluto the evolution of the outflow material at the inner radial boundary of the Pluto domain by best fitting the time behavior of the angle average fluid variables computed in that region during the Barnstone merger simulation used as reference. And also, we every 50 milliseconds, we substitute the outflow data computed by Pluto during the time extrapolation, which are causally connected with the one computed at the inner radial boundary of the Pluto domain. And we substitute this data with the ones coming from the self-constituted Barnstone merger simulation. This procedure allows us to reach in Pluto the final time of the Barnstone merger simulation, which is 250 milliseconds after merger, with an environment that is self-consistently reproduced up to a spatial scale that is about twice more larger than the one covered by the Barnstone merger simulation used as reference. And from this point, we extrapolate for other 100 milliseconds with Pluto. At this point, 350 milliseconds after merger, we include an intermediate phase of 30 milliseconds in which we mimic the formation of an accretion process at the center, which starts to power the in-space gamma reverse jet. And we do this using the same procedure that the same prescription that we presented in our previous paper, but now taking into account also for the presence of magnetic fields. So at 385 milliseconds after merger, we perform the jet injection by artificially. And in particular, at this time, the post-merger environment has the properties that you can see in the plots on the right. In particular, it has a very high thermal energy close to the center remnant. And it has also a quite uniformly distributed magnetic energy density, also up to quite large scales, which leads to magnetic dominated environment at a larger scales. To perform jet injection in this simulation, we adopt a more realistic prescription, so a structured jet. And the prescription was inspired by the one presented in March 2015, which we adapted to our coordinate system. And in particular, we set the initial jet with the both poloidal and toroidal magnetic fields, with rigid rotation and with transversal equilibrium. Moreover, compared to our previous jet simulation, we increased the initial jet to side luminosity up by 1 order of magnitude, and we set the jet magnetization to 8%. So these are our results of this new jet simulation. In particular, here you can see 3D renderings of the jet cocoon structure at 3 different simulation times. In particular, at the center, you can see the structure at the time of jet breakout. And eventually on the right, you can see the final jet cocoon structure, which is computed at about 1 second after jet launch. This jet is very different compared to the one obtained in our previous aerodynamic simulations. In particular, his properties are shown in these plots on the left. And you can see that now the jet is much more collimated and also much more stable along the main propagation axis. And we think that this is the result of both the more expanded, more massive initial environment in which the jet propagate, but also it could be also the effect of the presence of magnetic fields during the simulation. You can also see that the thermal energy density is follows the jet propagation due to energy transfer, but instead the magnetic energy density is mostly confined inside the environment instead of into the jet, and this is due to the fact that after the breakout, the magnetic field dissipate very quickly. And here you can also see some angular properties of our jet, which are the profile of the beta gamma average on the azimuthal angle. And also here you can see the angular profile of the isotropic equivalent energy, which reaches maxima of about 3.5 10 to the 50 eV. Here you can also see which is the magnetic field structure of this jet at the time of breakout. And the magnetic field is very chaotic, quite not ordered. And so now we are analyzing our results of the simulations, and we will publish them soon in a paper. And then we will start to perform a parameter investigation in order to understand the role played by the several free parameters of our model in the overall jet evolution and the final jet structure. And in the next future, we will start to provide more quantitative results using adaptive mesh refinement algorithm for the numerical convergence of our results. And then we will start to apply semi-analytical models and numerical algorithms to predict the prompt and afterglow emission of the simulated short gamma burst jet. So for the moment, that's all. And if you have any question, please ask me. Thanks.
Okay, thank you very much, Andrea. Very interesting. Okay, so are there any questions both for Jay or for Andrea? Please raise your hands. Okay, let's start with Julian.
Okay, very interesting work presented here. I'd like to understand better the procedure for initializing the magnetic field in these jet outbreak simulations that Andrea just described. I may have misunderstood what was being said, but it seemed to me that the base simulation from Spritz was already an MHD simulation. But when the data were transferred to Pluto for the jet propagation part, the field was substantially amplified. And is that correct? And why did you do it?
Yes, it is correct. So the magnetic field of the environment is self-consistently computed during the Barnard merger simulation, and instead we model manually the magnetic field profile of the inspect jet. But I want to show one thing. Can you see my slides?
Yes.
Okay, so of course, one of the main goal of us is to implement a jet which is self-consistently launched during the Barnard merger simulation and imported into the Pluto code for the large-scale evolution. And to do this, I want to stress this technique that we use to extrapolate the evolution of the BNS data in Pluto is quite promising, because we can, if we have a jet that is self-consistently producing a BNS merger simulation, as the one shown by my colleague Jay in the previous talk, we could import this jet directly into the Pluto code and extrapolating their evolution for longer time scales than one covered by the Barnard merger simulation, substituting the self-consistent data computed during the simulation. But these the procedures allow us to cover largest spatial scales that one covered by the Barnard merger simulation. So in this case, if we will be able to do this, our jet will be implemented self-consistently.
So why exactly did you amplify the field? What was the justification? In the volume that actually overlapped between the two parts of the simulation?
Sorry, can you repeat the question, please?
Okay. I understood you to say that in the volume in which you had data from the first simulation,
Yes.
and now you're covering in the second one, that the field strength was increased significantly in the process of that injection.
where do you see this magnetic field amplification?
Okay, that's why I said you seem to say that it was you put in a stronger field, 1016 Gauss. And so are these two simulations in fact consistent in the volume of overlap?
So you're saying
maybe I can provide some clarification on this. So I think Andrea is using the simulation data from a previous simulation by Whiskey MHD, and this was done by Dr. Chalfie in 2020, and this did not produce any jet. So while the results I showed, which are recent with Spritz, they have some collimated outflows, but we haven't used this data in Pluto yet. So I don't know if there's a confusion because of that.
Can you say again then how you do this handoff? I think maybe there is a misunderstanding there.
Right, so the handoff is done between this Whiskey MHD simulation data, and that does not have any jet, but it has a magnetized BNS environment. So there is no jet produced in this, but we do have this ejecta that is produced by this massive supermassive neutron star remnant. And in that ejecta is basically imported to Pluto. And then in that ejecta, now we by hand put and inject a jet.
Ah.
Yeah, so
Yes,
there's
that's exactly what I was asking about. So what
Right,
is the justification for doing this?
Because in the current Pluto simulations, we want to evolve a jet in this magnetized BNS environment, which is different from the typical approaches where you just put an environment by hand, which could be spherically symmetric, which Andrea talked about. Maybe.
Okay.
Yeah, we are studying.
So the jet is inserted by hand.
Yeah, it's a model. Yeah.
This model.
Right.
That's what I wanted to clarify.
Yeah. In the future, we want to take the jet from, like, say, the Spritz simulations, and then put the jet directly. And then we don't need to put the jet by hand. That's it. Yeah. Thank you.
Okay.
Thanks a lot.
Thank you, Julian. Vasilios?
Hey, very nice talk. I have a question for Jay, actually, for the first talk. How do you choose the strength of your KO dissipation? Because I think you have to be really careful in order to not quench the growth of the magnetic field and all that by doing that. Do you have a systematic approach to that, or is it mainly just looking at oscillations and saying that the A field looks smooth enough and that's enough KO?
All right, that's a good question. So I would like to also mention this, that currently in Spritz, we use the generalized Lorentz gauge for involving the AWAC, but for the computing the magnetic electric fields, we are having this flux constrained transport approach. And for this, we found some instabilities in the magnetic field, and while during the evolution, producing some spurious results. So for that, we add KO dissipation. While I think when simulations are performed with Illinois JMHD, they use Upton CT scheme to compute the electric field. And in that case, they don't need KO dissipation. So that's one clarification. So we are now in Spritz trying to implement this Upton CT scheme and such that we don't need this KO dissipation. But when applying this KO dissipation, we don't have any particular approach. We use the standard value of this dissipation parameter epsilon of 0. And this, I think the value is about 0.1. So we haven't done like a parameter study of how this value has been used previously with Whiskey MHD simulations. So this did not, so we just took that, but yeah, we have to probably look into this in detail to understand how this could affect magnetic field evolution.
Okay, thank you.
Thank you.
Okay, thank you, Vasilios. Amir?
Yeah, I just want to follow up on Julian's question. The conventional wisdom is that the jets in these systems produced by Blunt-Rosenheim mechanism or by neutrino, because if it's by Blunt-Rosenheim, then it's high sigma jet. So Pluto is irrelevant here. You'll need probably a different code to simulate high sigma jets. So I'm just trying to understand the general picture here.
Yes, I know that the Pluto code is also able to deal with high magnetized systems, but yes, I really don't know which is the typical magnetic field of a jet produced during the Bradford mechanism. But in our Pluto simulation, we import this jet produced in the BNS merger simulation into a system which has a more larger scale. And so maybe at that scale, the magnetic field is a bit reduced compared to the point of launch.
But you have a hydrodynamic jet, right?
No, the last simulation was with magneto-hydrodynamic jets.
But weakly magnetized, not high sigma.
Yeah, it was 80% magnetization.
Okay, thank you.
Okay, thank you, Amir. Do we have more questions? I don't see hands raised. I have a short question for Jay. Do this magnetic field out of the stars leave an imprint on the gravitational wave, or is just is negligible for compared with gravity?
Right, so that's a good question. So from what, in my knowledge, these initial fields should be dynamically unimportant, so might not have an imprint on, say, the initial configuration might not, but one also has to understand how high you can push these fields. So can you impose a 10 to the power 17, 10 to the power 18 Gauss fields, which is probably unphysical or unreasonable? That was one of the questions. So that might, I don't know, cause some kind of deformation in the neutron stars or not. This is something that we haven't looked at, but at least 10 to the power 6, maximum 10 to the power 16, which has been also seen in previous simulations by Dr. Chalfie, should not have a direct impact on the dynamics, so the gravitational waves.
Okay, thank you.
Thank you.
Okay, so I don't see hands raised, so we can take a break. I'm sure everybody.
But I just
Yeah.
have a question though before we take a break.
Sure.
So you guys seems to stop the simulation of 50 milliseconds. Is that correct? 50 milliseconds. Is there just a question of resources, or is there just any other reason?
Right. So we are struggling a bit with resources too. So that is one thing as well, that for the BNS simulations with spreads. So we are for now going up to say 50 to 100 milliseconds and exploring different initial magnetic energies to see what can possibly produce such incipient jets. So yeah, for now we are doing short simulations and not long term. But yeah, eventually once we have more resources, we would extend these and also use higher resolution.
Okay, so it's just a question. Okay, thank you.
Thank you.
Okay, thanks, Manuela. Okay, so let's take a five. Well, first of all, thanks again, Andrea and Jay. And
Thank you.
very interesting.